What's up, stat heads? Let's go ahead and get into some discrete and continuous random variables. Here we go. A random variable takes a numerical value that describes the outcomes of a chance process. The probability distribution of a random variable gives its possible values and their probabilities. The little diagram you're seeing right here is just showing you that basic idea. We have values that would be your x values, and they would typically appear as whole numbers across the top in this case, maybe 5, 7, and 2, and the probability right below them, the p sub 1, p sub 2, p sub 3, those are your individual probabilities associated with each of those values. So for instance, a value of 5 has a 10% chance of happening in this little purple representation of those numbers right there. The probability distribution for a discrete random variable x lists the values x sub I and their probabilities p sub I, which is again what you are seeing right here. For the probability distribution to be valid, the probabilities p must satisfy two requirements. The first requirement is p is a number between 0 and 1. The maximum probability of an entire distribution would be 1. The lowest probability would be 0. So your individual probabilities should be between 0 and 1. And then lastly, the sum of the probabilities is going to add up to 1 if you add them all together. There are only 3 probabilities shown in this little diagram, and the representation right there does have a ... implying there could be more than 3 probabilities. So let's just take a look at an example that hits that idea. High school students in Michigan sometimes get snow days in the winter when the roads are so bad that school is canceled for the day. Define the random variable x equals the number of snow days at a certain high school in Michigan for a randomly selected school year. Suppose the table below gives the probability distribution of x. Part A. Write the event the school year has 0 snow days in terms of x, then find its probability. Here's what that looks like. You write it as P of x equals 0. This is saying the probability that x equals 0. That is how you write the event. This is how you show work. This is the proper procedure that you're going to want to do throughout this entire chapter when you show your work. Define your probability showing P parentheses and then whatever it is you're looking for. Maybe it's a specific value like x equals 0, or maybe x is greater than 5, maybe x is less than or equal to 4. You just need to write that down to properly show your work. To find the probability, it is quite easy. We do not know the likelihood that there are 0 snow days, but we know the likelihoods of all of the other amounts of snow days. And since the entire distribution has to add up to 1, we can take the number 1 and subtract the sum of all of the other probabilities. And in order to show work for that, I chose to again use the ellipsis technique because it is something worthwhile to do in this chapter. There's just an occasional time where there will be a lot of probabilities to list, and once you establish the pattern that you're doing, feel free to use an ellipsis just to show the and so on and so forth idea. So you can see the 0.19 is for 1 snow day, 0.14 is for 2, so on and so forth. You do all of the arithmetic, subtract that from 1, you're going to get 0.33. So that is the likelihood that there are 0 snow days in a particular year, 0.33 or 33% chance. At this high school, if more than 5 snow days are used over the course of the year, students are required to make up time at the end of the school year. What's the probability that a randomly selected school year will require makeup days? The key word, more than 5 snow days. So when you set up your work, you're going to want to show the probability that there are more than 5 days. So x is greater than 5, and then go ahead and make that calculation. Greater than 5 means you would take 6, 7, 8, 9, and 10 snow days, and you would add all of those values together, which would give you 0.12. Part 1b. Another snowy day in Michigan, displaying a probability distribution. Make a histogram of the probability distribution and then describe its shape. Making a histogram is very easy to do. You would start by looking for your lowest and highest probabilities. Since the event of 0 snow days carried a probability of 0.33, we would want the histogram to go up to a height that is at or more than 0.33, so I chose to use 0.35 right there. And then along the x-axis, we just have 0 all the way to 10 snow days, and then just draw the bars to the corresponding heights, starting with 0 snow days. That would be a height of 0.33, which I have now written down right up there in purple. Take the rest of the probabilities going from left to right and just draw the corresponding bar heights. Like one snow day would be 0.19, so I went up to approximately a height of 0.19. As you keep doing this, you wind up getting a graph that has a shape that is skewed right, and when dealing with probability, we want to be looking at the mean as our measure of center, not the median. When you're dealing with probabilities and the expected value of a distribution, it is the mean we are looking for, not the median. So that's something you can always tell yourself in this situation. Regarding the variability, when you describe its shape, the standard deviation is what we will be examining in this chapter. So if you remember from earlier on in the year, SOC V, that's just a way to help organize your thoughts when you are describing the shape of a distribution. What is the shape, the center, and the variability, and include the context as well. Let's go ahead and look at another problem. So the mean or expected value of a discrete random variable is its average value over many, many repetitions of the same chance process. Suppose that x is a discrete random variable with probability distribution, and we have the same diagram that we were looking at before. To find the mean or the expected value of x, multiply each possible value of x by its probability, then add up all the products. Very easy to do, and this is a formula provided on the formula sheet. Quick couple things to notice. We are going to be looking at mu, the population mean. We're not looking at the sample mean, it's the population mean. So once upon a time, we talked a lot about x bar. That's not the main focus for the mean in this chapter because that is the sample mean. We are looking at the overall population mean, which is going to be mu. The way you calculate this, go ahead and just take each value and multiply it by the corresponding probability, and then add that answer to the next value multiplied by its corresponding probability. And all of the color coding should help you see that there's x1 times the first probability, which is right there, plus x2 times the second probability. You repeat this process until you have all of the probabilities dealt with, add them all together, and you will have the expected value. And this is again something that can be done on the calculator. You have a formula for it as well. It's pretty easy to do, but right at the bottom, before we do a sample problem, make sure you take down how to write and interpret the mean as a statement if you were to respond with it. This is incredibly important because it is the way you will answer this question to guarantee yourself full credit on any related exam. You would say, in many, many, and then include the context of the x value, in many, many blanks that are randomly selected, we'd expect the, again, include the context of the problem, to be around or about or approximately whatever the value of the mean was. This statement is the sentence builder for how to respond to the interpretation question. Let's now look at an example of that and put it to action. Buffalo Wild Wings ran a promotion called the Blazin' Bonus, in which every $25 gift card purchased also received a bonus gift card for $5, $15, $25, or $100. According to the company, here are the probabilities for each bonus gift card. Let X be the amount of money won on the bonus gift card. We have 4 values in our probability distribution, and we are being asked to calculate and interpret the expected value of x. Now, this would be a good time to perhaps pause the video, go back and look at the formula and try to implement it yourself. But if you're not going to do that, here is what the first answer is going to look like. You would take your first value being 5, and you would multiply that by 0.89, which is the probability that went with it. Take that value and then add it to the second value of 15 times its probability. And that gives you some product, and then continue on for the blue and purple values that are at the end of the probability distribution. If you do all the math correctly, you should have gone $6.37, and that is going to be the expected value of this distribution. Right below that, you're going to see the interpretation, and it's already written out, so really try to absorb the sentence builder idea that was described on the previous slide. In many, many gift cards, that's the context of this problem. In many, many gift cards that are randomly selected, always include that part. You're establishing that they were randomly selected. We would expect now the full context, the amount of money won on the bonus gift card to be about $6.37. It is in your best interest to write out this statement exactly as it appears. Choose whatever word you want for around, about, or approximately, or on average. Any of those words are perfectly fine. Just choose one, run with it, and write your response like this every time. It's going to get boring. You're going to sound like a broken record, but it is guaranteeing you maximum value on the interpretation questions. Right below, you're going to notice there are calculator procedures that are now being shown for how to do this, because some of these problems will require you to write out many, many values, and doing the calculation by hand like this, it's not a great use for your time. Here is the basic idea of what you're going to be doing, but I'm not going to take time in this video to dive into the calculator procedures. I'm just going to let you know they are right here, and in class, we are going to go over how to use the calculator, and if there is time, a video will be made also breaking it down. So one good reason to appear in class so that you can learn how to properly use the calculator, which is going to save you a whole lot of time. All right, let's keep moving on. The standard deviation of a discrete random variable measures how much the values of the variable typically vary, that's the key word, from the mean. And then once again, we have our probability distribution model of x1, x2, x3, and the three probabilities that go with it, and that the mean of x is mu sub x, and then the variance is the very involved formula that you are now looking at. Here are some things to jot down and observe. The basic flow of this formula, I will describe it once, and then you can allow the calculator to take a lot of the heavy lifting off of you. So the way you calculate the variance is you start by taking your first x value and you subtract the mean from it. That quantity then gets raised to the second power, and then after you raise it to the second power, you multiply it by the first probability. It looks involved, but it's very repetitive. You can see with the second piece of this, it's just asking you to do the same thing. Take the second value, x sub 2, subtract the mean from it, raise that to the second power. And when you have that answer, you multiply it by the probability that goes with the second x value. Yes, it does get tedious, but that is why the calculator is going to make your life a lot easier with this procedure. It's still important to recognize the formula. And since you are adding all of these individual pieces together, sigma, the summation notation, which is the backwards E thing, can be used for this representation. That is going to give you the variance. We are looking for the standard deviation. And it has been explained earlier this year, in a previous video at least, that the standard deviation is the square root of the variance. So you literally take this involved formula, and then you take the square root of it, and you will have the standard deviation. And again, this formula is appearing on your reference sheet, so it is something you can refer to there. Let's go ahead and do a problem highlighting this idea. And, before we get into that, once again, make sure you take down the proper way of interpreting a standard deviation problem. Just like with a expected value answer, you would start by saying, if many include the context, items are randomly chosen, we'd expect the, again, include the context, to typically vary. That's the key word. Words typically vary by whatever the standard deviation's value is from the mean, and then restate the mean's value. Let's go ahead and put one of these into action so you can see how the interpretation comes into play. It's actually already at the very bottom, but we'll get there in a moment. Calculate and interpret the standard deviation of x. Here's how you can start it. The formula, carry over the mean from the previous problem, because we will need that. The formula begins by taking the first x value, in this case 5, you subtract the mean, which was $6.37, square that difference, and then multiply by the probability of the first value occurring, which was 0.89. That chunk of math gets written down, and then you repeat that pattern for the second value, which I, again, am representing with a ... just because it does get tedious writing it out. So what you could possibly do is pause the video right now and just set up what that last one involving the 100 number is going to look like, because that's what is going to appear in a moment. And here it is. So 100 minus the mean squared, multiply that by the probability of 0.02, and when you add all of those four products together, you're going to have 29.97. This is much more quickly done with the calculator, but we will get to the calculator procedures at another point in time. Since the variance is the square of standard deviation, we need to go ahead and take the square root of 29.97 so that we can get the standard deviation. The variance is is always the standard deviation squared. So we have to take that square root, and that will give us a value of $5.47. It is in your best interest to use the calculator commands for doing standard deviation. They will be explained in class, so please attend class so you can get that knowledge in your head. And then right at the bottom, the interpretation of standard deviation using the correct sentence builder. If many gift cards, there's that context, gift cards, are randomly chosen, we would expect and the whole point is money, the amount of money won on the gift card to typically vary. Very important you include typically varying. That's the whole point of the standard deviation concept. Typically varies by $5.47 from the mean of $6.37. Write it this way every single time. You will never miss an interpretation question if you use this sentence builder. All right, one more concept. A continuous random variable can take on any value in an interval on a number line. Previously in this video, we've been discussing discrete random variables where decimals and fractions have not been involved, but with things being discrete, there are also things being continuous. So, how to find the probabilities for a continuous random variable? Here's what you do. The probability of any event involving a continuous random variable is the area under a density curve and directly above the values on the horizontal axis that make up the event. Hopefully this sounds a little familiar because this is the beginning of when the normal model and the normal distribution was first introduced. And what we're trying to look for, the probability, is the area under the bell curve. So in these situations with continuous random variables, you are going to default to finding the z-score, which we will do on the very next example. But the one we're going to look at right now is actually quite easy, so maybe pause the video, try reading it on your own and seeing if you can get that answer. Mrs. Raines is feeling generous one day and decides that each student deserves some extra credit. She assigns each student a random extra credit value between 0 and 5, with decimals including, by using a random procedure on the calculator. Let x equals the amount of extra credit for a randomly selected student. The probability distribution of x can be modeled by a uniform density curve. Keyword uniform. Now you know it's going to be the same shape. It's not going to be a bell curve. A uniform density curve on the interval from 0 to 5. Find the probability that a randomly selected student will get more than 3 points of extra credit. Here is a representation of that. We have a rectangle that is uniformly distributed. We are going to make individual fifths of that rectangle because the assignment of values was between 0 and 5. And then since we are looking for the probability of getting more than 3 points of extra credit, we would be interested in the probabilities that are more than 3, that being the numbers 4 and 5, which each had a 1/5 chance of occurring. So the probability of getting x being more than 3 is equal to adding up the probabilities that x is equal to 4 and 5. 1/5 plus 1/5 is 2/5, which reduces to 0.4 in decimal form. Pretty easy idea. Let's now finish by looking at one that's going to involve us dealing with z-scores and the normal model. Here we go. Weights of 3-year-old females. The weights of 3-year-old females closely follow a normal distribution with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. Suppose we randomly choose a 3-year-old female and call her weight X. What is the probability that she weighs at least 30 pounds? We have not done z-score related things in a while, so if you remember how to do it, maybe pause the video, give it a shot. Otherwise, here we go. It says at least 30 pounds. So the probability we are looking for is that P is greater than or equal to 30. Now, that is going to involve us using the z-score. The formula for finding the z-score is you take your observed value, x, in this case 30, you subtract the mean, which they told us was 30.7 in the text, and then right below that, you are going to divide by the standard deviation, which was also told to us as 3.6. This is just using the z-score calculation formula that was first introduced, I believe, in Chapter 2. You do the arithmetic, you're going to get negative 0.19. Now you need to go to the z-table and find the corresponding probability that goes with 0.19. It said we're looking for at least 30 pounds. So at least means it's going to be more than 30. So what you're seeing in this little diagram, mu, the mean, is 30.7. So 30 is a little below 30.7, so that's why I drew the little flag just to the left of the mean. Since it says at least 30, I shaded above the flag of 30 right there. But what we need to remember, the z-score is giving you the probability that is below your target value. That's just how the table is set up. The 0.4247 number that you would get from the z-table, that is corresponding to the probability that you do not want. It says at least 30 pounds. So if 0.4247 is everything below 30 pounds of weight, then we would need to do 1 minus p, because again, 1 is representing everything in the probability curve. 1 minus p to get the correct answer of 0.577, which is something that you could also get by using calculator procedures that will now, again, be taught in class. You can see those procedures right down here at the bottom, as well as the NumWorks calculator, the other acceptable calculator for this course, but those things will be discussed more in class, and this is just meant to be an overview of the basic ideas with the first section of the current chapters. So, thank you for watching. Hope this helped. Drop a comment if you have any questions, and I will see you in the next video.